Hello physics students, this is Dr. Brinzi here. This is lesson 5.2.2, and our objective for this lesson is that we're going to be able to use this thing called moment of inertia to explain why it's more difficult to swing a baseball bat from its handle rather than from the thick end of the bat. So if you're familiar with a baseball bat, which I'm guessing many of you are, but maybe some of us aren't, you would know that it's kind of shaped like this, and oh my goodness, here I go for my crazy drawing. Let's try that again. You have a small handle here, and it's very thin, and then as you get closer to the end of the bat, the opposite end of the bat, it gets thicker, and yes, I'm exaggerating this. And then you usually hold on to the left end of the bat, this end right here with the little knob on the bottom, and you attempt to hit the ball with this end of the bat. So why would it be harder to swing a bat when you're holding it by this end than when you're holding it by the thick end over here? Well, that's a really good question. Now, in order to explain this concept, I want to go back and talk about inertia. When we were in Unit 2, when we were talking about Newton's laws, we found out, or we came across the idea, that it's a lot easier to push a box on a surface with a small mass than it is to push a box with a big mass. Okay? So if you were to ask which one of these two has more inertia, which box would it be? Would it be little m or big M? Well, the answer is big M. If you remember what inertia is a resistance to change in motion. Ugh. I'm having a hard time writing on my pad right now. Inertia is an object's I should have an apostrophe, resistance to change in its motion. So if we applied a force F to this box, and we applied the same force F to this bigger box, we would notice a much bigger change in this box's motion than we would observe in this box's motion. In other words, this box is going to accelerate faster than this box would. Well, can this happen with rotation? When you're rotating something, are some objects harder to rotate than others? Well, the answer, I think, will be pretty obvious if we do a little thought experiment here. So let's take a piece of string, and I'm going to take a piece of string here, and I'm going to put a ball at the end of it. And then imagine picking up that piece of string and then trying to, so you grab onto this end of the string and then you try to twirl it above your head. Okay. It takes some effort to do that. Now imagine that we take that same string, same mass or ball attached at the end. Now let's try to grab it, say by, let's grab it right there. So we grab the string right here and then we twirl it above our head. Now, which one do you think is going to be harder to keep in motion? Is it going to be this one up here, or is it going to be this one down here? Well, if you want to do this little experiment yourself, you can go ahead and try it. But if you don't have these things available, I would imagine that it would be a lot harder to, it'd be a lot harder to rotate this string or twirl this string above your head than it would be to twirl this above my head when I'm holding it from here. So, this would be harder to rotate. And this would be easier to rotate. Now, even though these had the same mass, it's obvious that we held it by a different position. So position, the position that you use to hold this string by affects how easy or hard it is to rotate this ball above our head. So we know it depends on the radius of our circle. A smaller radius tells us that it's easier to rotate if all other things are kept the same. And hopefully you would quickly realize that if we had the same length of string but decided to attach a bigger mass to it, then would it be easier or harder to rotate? Well, it would be harder to rotate, right? So it depends on radius and mass. So the higher the mass I have, the harder it is to rotate, and the bigger the radius, the harder it is to rotate. As a matter of fact, if you were just talking about rotating a mass on a string and you ignore the string itself, if my ball, my point, has a mass of m, and I am twirling it from this end or rotating it from this end, so I have a radius of my circle r, then it turns out that you can write something what's called moment of inertia. That moment of inertia is I, and it is equal to m r squared. Okay. Now that's for a single mass going around a circle at a radius r. So this thing called moment of inertia I should have defined it before I gave you the formula, but I didn't. So moment of inertia is an object's resistance to change in its rotational motion or its circular motion. So the higher this moment of inertia is, the harder it is to rotate that object. In other words, that object has more resistance to change in its circular motion. Let's see here. I think I have an extra slide here. Now, not only can you calculate the moment of inertia for a little point mass or a single mass on a string, you can also calculate the moment of inertia for objects that we encounter in the real world. Now, in order to actually be able to calculate these things, we have to use some pretty advanced calculus. So you're never going to have to derive an equation or figure out an equation for a long rod or thin rod like this, but if you use some really advanced calculus, you can find out that the moment of inertia for this rod, when you rotate it about this axis, is m times L squared, where L is the length of the rod, divided by 12. Now, a funny thing is that if you decide to rotate this rod around the end, so if you decide to hold it by the end and twirl it in the air, it's going to actually be harder to rotate than it would if you held it by the middle and tried to rotate it around this axis. So, moment of inertia depends on the axis of rotation you use. This is something unique about moment of inertia that we don't see with inertia in a straight line. Axis of rotation. So it depends on where I am holding the object when I rotate it. And that's also true of point masses. Because after all, with a point mass, if you hold it close to the mass and twirl it around, that's going to be easier to rotate than if you held it a long way away from you and tried to twirl it around your head that way. So moment of inertia depends on the axis of rotation you use. So if you ask me for a formula for moment of inertia, like what is the moment of inertia for a thin rod, I would have to ask you, well, what is the axis of rotation you're using? Are you trying to rotate it around the middle? Or are you trying to rotate it around the end? Or you could even say, well, I'm trying to rotate it around this axis right here, which would even have a different formula for moment of inertia. So here's some other objects that you want to write down for a moment of inertia. So we have a cylinder. So if you have a thin cylinder here and you're trying to rotate it about this axis in the middle, so in other words, it's spinning around and around like this. Okay. And if it has an inside radius R1 and an outside radius R2, you can use this formula to calculate its moment of inertia. Now, if this cylinder becomes really thin, and it becomes so thin that we can say that R1 equals R2, or it's very close to it, I should put approximately because we never encounter objects in the real world where. So if we can say that the inside and outside radius are almost the same, well, what that becomes, you'll notice that I can replace R2 with R1. So let's do that. R1 squared. Well, it looks like I have I equals m over 2 times R1 squared plus R1 squared. Well, that turns out to be m, sorry about that, m over 2, I was about ready to skip a step, times 2 R1 squared, and this 2 and that 2 divide out, and it turns out your moment of inertia of a thin cylinder is m times its radius squared. So there are a lot of these formulas that you either have to memorize or you have to refer to on a sheet. I actually just refer to them on a sheet usually. You'll definitely want to remember the one for a point mass. Definitely want to remember that one. Okay, so definitely remember for the moment of inertia for a point mass. Here's some other objects you can copy down. A solid sphere. So this is a sphere that has mass from the center all the way out to the edge. Its moment of inertia is 2/5 times its mass times its radius squared. But if you make a thin, in other words, if you hollow out the sphere so that the only mass is on the shell itself, in other words, it's hollow inside, so if you went dunk, 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 if you knocked on this one, it would have an echo to it. Well, its moment of inertia ends up being 2/3 times mr squared. Okay. So, which one of these two is going to be harder to rotate? Well, I know that 2/3 is greater than 2/5, so believe it or not, if you have a hollow shell with mass m, it is going to actually be harder to rotate than this solid sphere that has a moment of inertia of 2/5 mr squared. So this one would actually be harder to rotate. Now that's assuming that the mass of the two are the same and the radius of the two are the same. Here's another moment of inertia for, let's say we have a rectangular plate and we're trying to spin it around its center right here. And it turns out that its moment of inertia is given by this formula right here. Okay, so if you are in advanced class, you have finished taking all of the notes that you need to take. But if you're in AP, we have a few more things to talk about. One of these things is called the parallel axis theorem. And what that says is that if I have, like say, a disk, some object, and it can be any object, but I'm going to draw a disk. I hope I'm going to draw a disk. That's a terrible looking disk. Oh, that's just as bad. I should have done this beforehand, but I didn't. Okay, so it has a radius r. It has a mass m. And if you look back on your formulas, okay. Okay, so that is the moment of inertia if I were to spin it around this axis right here. Now let's say that I decided instead, well actually let's call this I1. Let's say I decided instead to attach this thing to a string, and I'm going to say that that string has no mass. Okay, I originally spun it around this axis, and I know the moment of inertia for that axis. But let's say that I attach this disk to a string that has no mass, and I decide to rotate it around this axis right here instead. So my new axis of rotation is a distance d away from my original axis of rotation. Now here's the cool thing about the parallel axis theorem. If I wanted to calculate the moment of inertia in this case, where I'm spinning it on this string, and it is a distance d away from my axis of rotation, I can figure out its new moment of inertia by taking its original moment of inertia and adding 1/2 times d squared. No, I'm sorry, 1/2 m times d squared. I almost forgot the m. So if I wanted to calculate what its new moment of inertia is, I can use this parallel axis theorem. And it will tell me that its original moment of inertia with this axis plus 1/2 md squared, where d is the distance between my two axes. Now this only works this. I better go with md squared there. And then better erase that. There we go. So this ends up being ml squared divided by 4, which is the same as 3l squared divided by 12. Whoops. Oh my gosh. What happened there? Yikes. Right at the end of my video, technical difficulties. What did I just do? All right, there we go. Whoops. Well, if you take 1/12 plus 1/4, you end up getting 4/12, which is the same as 1/3 ml squared, which is the moment of inertia of this rod right here. Okay? So the parallel axis theorem shows you that you can actually use this moment of inertia to figure out what this moment of inertia is. So in reality, if you know the moment of inertia about any axis, you can figure out what its moment of inertia is about any other parallel axis by using the parallel axis theorem. And we're going to have an opportunity to practice that in class tomorrow. And I'll look forward to seeing you then. Bye.